that. Yeah. So, okay, for our recording sake, let me just quickly go through so that later if you hear, you will know the whole story. So we have certain values on, we are considering this empty curves data set. And in the empty curves data set, we have these miles per gallon. So we have these values like 10.4, 29.8, 16.3. So on an axis, we call it x-axis for some time, and we just plot the miles per gallon. And some of the observations that we have seen here in the data set, we plot them with the red dot. Then we create some beans, and then we calculate how many points are there in that beans. Okay, and suppose in this beans there are 3, in this beans there are 5s, there are 7 points, there are 5 points. In this way, we calculate the bean, the counts, the number of points that are there in the beans. Now we just, so here is the frequency. So this is the 3, this is the 5, then this is the 7, this is the 5, 4, 3. So that's how we calculate we draw the histogram. So histogram tells us gives us some sense of the distribution, but it really doesn't tell us how the probability distribution is connected and how the concept of probability comes in here. So what we do, so here I will just introduce the concept of probability, just basic definition. The empirical estimate is basically, if I am interested in probability, what is the probability that value is between, say, 10 and, just a minute, hold on. So suppose you are interested in, suppose this bean is 10 and this bean value is, say, maybe 15. Okay, so I'm interested in what is the probability that if I randomly draw a sample, that miles per gallon for that sample will be between, say, 10 and 5. Now this, they will say that, okay, we can say that, okay, sorry, 10 and 15, sorry, 10 and 15. So what we will do, we will just count how many cases are there. So that is 3. That is 3 divided by total number of cases. So 3 plus 30, 15, 20, 24 plus 3, 27. So this will be our estimate, but these are called typically empirical estimate. Empirical estimate. This works well as long as we see some data points. But what about the probability that we will see a sample whose miles per gallon is between 5 and 10? Is it 0 by 27? What do you think? Any idea?
Sir, you mean for different sample?
No, this is the only sample that is you have.
Yeah, so for this sample, empirical estimate is 0.
0. So you will probably we will just do the 0 by 27, right?
Yes, sir.
Okay. Do you think that estimate is correct?
Sir, for this sample, empirical estimate is correct, but population estimate is not correct.
So that means you are saying that this sample has some kind of limitations.
Yes, sir, sure.
Blind, so we say blind statistics has some limitations. If you just use empirical estimates, these are also called empirical estimates, have some estimates have some limitations. So you cannot apply empirical estimates blindly. That is where the integral calculus comes into rescue. Okay, and how we solve this issue. So we will do another tweak in this case. So what is that case? What we will do? So we'll one more before we move. I'll just pose one more thing here. Typically, when you will see that histogram, generally we take the equal beam width. Typically, we take equal beam width, but you don't have to always take equal beam width. In fact, if your data is highly positively skewed or negatively skewed, or data is skewed in one side, you may have to take larger bandwidth at the tail side and smaller bandwidth at the body. Okay, so if this is the case, so then the same thing you can draw it in, say, with 4. So how many beans we have taken here? 1, 2, 3, 4, 5, 5, 6. But I can draw the same with 4 beans, and the 4 beans will look somewhat like this. With the same data, if I just change the bin width, the distribution behavior will change. Clear? Even with the equal bin width, if you just change the little bit the bin width, like so you decide to take the equal bin width, but you instead of taking 5 interval of equal to 5, you decided, okay, I will take interval equal to 7.5. Okay. As soon as you do that, the distribution, the way it looks, will change completely. Okay. So how we solve this issue? One way of solving this issue is on the so basically if you on y-axis, if you take frequency count, then your histogram will be sensitive to your choice of bin width. Okay. Now, how we solve this problem? One way to solve this problem is on the y-axis, instead of plotting the frequency, you plot frequency density. What does it mean? On y-axis, to solve sensitivity, to solve this issue, on y-axis, we plot frequency density. So how we solve this? So what is frequency density? I will define right away. What is frequency density? So let me put say x1, x2, x3. So these are suppose different beams, xk, and you are counting the frequencies, say f1, f2, this way up to fk minus 1. So these are the frequencies. Or easiest to, I think it is typical thing is 0, 1, 2 up to k. Then we will solve this issue of indexing. Then it will be. So basically, if you have for the beam width, what will be the beam width? W1 is x1 minus x0. Okay, and W2 will be x2 minus x0. W3 will be x3 minus x0. In this way, Wk will be xk minus xk minus 1. And corresponding to each beam width, you have the frequency count f1, f2.
Sir, I think W1 and W2 has some error. X2 minus X1 could be there, right?
So x2 minus x1, x3 minus x2. Yeah, thank you. Thank you. So this f3 is the frequency corresponding to W3 or this thing. And the same way, I don't know how to fix it. Fk. Now frequency density is effectively Fk by Wk. That is what we call it frequency density. Frequency divided by its width. Okay. If you plot frequency density on y-axis, then which is basically Fk by Wk, then can you tell me what will be this area representing? How you can calculate this area? It will be Fk by Wk times Wk, right? Are you guys with me?
Yes, sir.
Very nice. So that will give me the frequency. So the area now representing the frequency. So if it is a frequency density, can we now what is probability, empirical probability estimate? The frequency divided by total frequency, right? So I can divide this frequency density divided by the total frequency. That will give me the probability frequency density or empirical probability density. Empirical probability density. What is that? Empirical probability density is if k divided by n times wk. Now what is n? N is total number of samples. Okay. Now what is happening? If you on the x-axis you plot your beams, on the y-axis if you plot the empirical probability density, then essentially what you are getting, you're on the y-axis you're plotting if k by n wk times wk. On the this is beam size is wk, on the x-axis is probability density, empirical probability density. This so as wk is cancels, your area is basically if k by n. So your area is relative frequency density. This is also known as not only empirical probability, it is also known as relative frequency density. This is either called empirical probability or empirical probability or relative frequency density. Now, two things happens. Now, typically, if you look into the what we can do, suppose again I'm going to the idea of a thought experiment that we have infinite amount of resources and be able to draw as many as samples. So that means my sample size is increasing and increasing and increasing. So I'm making it to infinity. If I have lots and lots of samples, then I really don't have to take a big width. I can do it very smooth, a very small width. So I can push W to go to 0. As I do that, so it will become the histogram will become very smooth and eventually there will be a smooth curve that you can think of. Now this, so we can say that this empirical probability density so this empirical probability density, if k by n times wk converge to some f of x as n goes to infinity and w goes to 0. This probability function, is called this function. So that means we can think of this smooth function is called probability density function. So this is called probability. Just a minute. Probability density function. Now, if so, and this is called relative frequency density. So as n goes to infinity, w goes to 0, my relative frequency density goes to probability density function. Okay. Now, if I'm interested in finding probability of x between a and b, so what I will do, I will integrate this function fx dx. So remember that. So basically, essentially what is happening here is my if I'm interested in is my screen just went off?
Yes, sir.
Just a minute, please. Any questions you guys have, then please feel free to ask me. I would not mind taking class. Taking more questions at this moment. If not, then I'll move on to the small part that is still left with. No, yes. No question? All right. So if you still have any question, always feel free to ask me. If not, then I'll go to next level of discussion. So this discussion is so far at a conceptual level that okay, if we have certain degree of data, certain type of data, we can draw histogram, we can make some sense of how the distribution is behaving. And if you in R or Python, you will see that when you're drawing a histogram, it will give you an option probability equal to false or true. If it says probability equal to true, if you say probability equal to true, essentially what they are plotting is empirical probability density. They're just doing this, binning, and then calculating the binning size, bin size, dividing the frequency count by the bin size and the total samples. And then they are just plotting that histogram. So they're on the y-axis, they are essentially plotting empirical probability density. Okay, or relative frequency density, whatever. Both are in statistics, typical stat book, it will be written as relative frequency density. Some more probabilistic book will write it as empirical probability density, but essentially this is the thing that they are plotting. Okay, and the concept is basically as we have more and more data, that means basically we can have smaller and smaller bins, and that tells us that there could be a function we can smooth there could be an underlying function. That function actually is somewhat We don't know what is that function, but there must be a function, smooth function. And this function is essentially, so this estimate will essentially converge to this probability. And that is the whole idea of, I mean, this estimate will converge to this function. And this, when we are trying to estimate the probability, this empirical probability estimate will converge to the true probability as sample size increases. We can say that as sample size increases, the empirical probability density will converge to the true probability density. Okay?
Sir, I have a question.
Yeah.
Sir, as n tend to infinity, like sample is getting converted into population in one sense, right?
Correct.
And the empirical PDF is getting converted into PDF. Like empirical probability density is getting converted into PDF. Uh,
Not
so,
converted, it is, yeah, I mean, converging. Yeah, okay, go ahead. Yeah.
sir, like if we are taking sample from the discrete random variable, then
Discrete is some completely different story. Discrete distribution is completely different story. I'm only talking about continuous random variable.
okay,
Okay.
okay,
Discrete random variable like counts, right? Like number of goals scored by a home team, or number of insurance claim in a particular month, right? Those are discrete counts. For that, we use like Poisson distribution, binomial distribution, and there we use the concept of sequence and series. That's a completely different, that goes to a completely different track. That uses the concept of sequence and series. Whereas when we are handling the continuous random variable, that time we are using the concept of integral calculus. Completely two different. So both are part of your analysis, your real analysis or calculus you can think of, but two different techniques. Okay.
yes, sir, got it.
So now question is,
Sir,
yeah,
in last class you asked us to plot a graph of the asteroid. So do you have to parameterize to plot it? I mean, otherwise it's not coming.
I didn't get your point. What is your point?
So you asked us to plot the asteroid x to the power 2/3 plus y to the power 2/3 equals to 8. So unless I'm parameterizing the curve, I'm not getting the graph. So do I have to parameterize only, or is there any other way to plot it in R or Colab?
No, no. What I plot a asteroid.
Yes, sir. X to the power 2/3 plus y to the power 2/3 equals to 8.
I am not sure what is your question.
So I'm asking if we have to parameterize the curve in order to plot it, or can we just plot it like if we take a value of x, then we write y.
Wait a minute. What I have asked in the class, what I have asked you to do?
To try to plot that, to plot the asteroid.
Which curve? Can we, I'm sorry, L1 and L2 now? Yeah, that's a different question. I mean, we are talking about something different here. Yeah, I understand, but that's a completely different question. How did you get in there, yeah? I mean, I'm discussing about some issues here, which is completely different. I'll talk about it. Okay, fine. You have asked me, I'll tell you, but please, I mean, maintain the discussion topic, yeah. You should have asked me at the end of the discussion. I'm not ending the discussion here. I still have something to discuss anyway. You just break my thought. So I had certain chain of thought. You just break my chain of thought. All right, so essentially what we have so far discussed that we have some distributions x1, x2, x some n samples we have from some distribution with probability density, which has a probability density function f of x. Okay, so these are all continuous random variable from a distribution which is a probability density function f of x. Now, typically what happens is we, based on certain properties of the problem, we try to figure out what kind of probability distribution function will be suitable. Okay. Can it be, can we think of that fx is PDF? I mean, this distribution is normal with some mean mu, some variance sigma square. Can it be gamma distribution with A and B? Can it be log normal with location parameter mu and scale parameter sigma? So different distribution you can think of, and if you know the essentially what is the distribution, then you can, and if you're interested in finding probability of A less than X less than B, then all you have to do in A to B, then whatever the PDF of normal, suppose you're assuming normal, whatever the PDF of normal, you do that fx dx and you will get the probability. But definitely you have to know mu and sigma square. If you know that, but most of the time, this is typically a probabilistic approach. Probability will tell that, okay, if I know what is the mu and what is the sigma square, I'll just solve this integration problem. My job is done. But in reality, most of the time, we don't know what are the parameters. Most of the time, we don't know parameters of the distribution. Parameters of the distribution. Okay. And then what you do is, that is where the statistics comes in. So basically, most of the statisticians are basically interested in that the typical problem will be that I have some samples. I assume that it is coming from normal distribution with some population mean mu and some population variance sigma square. I don't know what are the values of mu and sigma square. Can we estimate mu sigma square using x1, x2, xn? So mu, so they will, so statisticians, they will first estimate mu and sigma square using x1, x2, xn. So basically mu will be some function of x1, x2, xn. Your sigma square will be some function of x1, x2, xn. We typically, we call it, we mark it as mu hat and sigma hat square. And then what we do, we just estimate, if I'm interested in finding what is the probability that x will be between A and B, we solve this problem assuming this is mu hat and sigma hat square. Okay. More proper way of making this. F of x given mu hat sigma hat square. So basically, I will just assume in that PDF, we will plug this mu hat and sigma hat square, and then we will solve this integration problem. So this is how typically, that is the connection between integration and, probability and statistics. Anyway, so I'll stop here. In 5 minutes, your quiz will start. So if you have any questions now, so that L1 to L2 norm that you guys are worried about. So what is the problem that, let me just stop the recording.